So the addition rule should look very familiar. We just did it like 10 minutes ago. So we're going to be looking in this section to things involving the probability of A or B. The probability that event A occurs or event B occurs. A compound event is any event combining two or more simple events. So the notation, the probability of A or B means the probability that in a single event, event A occurs, or event B occurs, or they both occur. So when finding the probability that event A occurs or event B occurs, you can, it depends on if you can't always do this, but you should find the total number of ways A can occur and the total number of B's can occur, but find that total in such a way that no outcome is counted more than once. So, the addition rule for probability. For any two events, E and F, of a random experiment, the probability of the occurrence of at least one of the events E and F is given as follows. The probability of E or F, the probability of E or F, is the probability of E plus the probability of F minus the probability of A and F, because, well, you counted this overlap twice. Or, I guess, doing A's and B's, the probability of A or B is the probability of A plus the probability of B minus the probability of A and B, because you counted this twice. Mutually exclusive events. Again, we call these disjoint sets. So A intersect B. If A intersect B is the empty set, then we say that events A and B are mutually exclusive. If the sets A intersect B is the empty set, then we call those disjoint. Those sets disjoint. As we've seen before, the probability of A intersect B, where A and B are mutually exclusive events, is just 0. So if this is event A, this is event B, and they're mutually exclusive, then the probability of A and B is 0, because they can't occur simultaneously. The addition rule for the probability of mutually exclusive events is, well, the probability of A or B is the probability of A plus the probability of B. So for mutually exclusive events, E and F, the probability of the probability of E or F is the probability of E plus the probability of F. The probability that event A happens only once. The probability of A intersect not B is the probability of A minus the probability of A intersect B. The probability that event B happens only once. The probability of not A intersect B is the probability of B minus the probability of A and B. The probability of neither of the events A and B occurring is as follows. Well, neither nor is a strange English construct. It says the probability of neither A nor B is the same as the probability of not A and not B Or you can think of it as neither A nor B as being the complement of the event A or B. So this is also equal to 1 minus the probability of A or B. So the additive rule for 3 events, the probability of A union B union C. Oh, I did it in unions now. Not that it really matters. Oh, I see, I did these in unions. Let me see if I did these in unions or intersections. It really doesn't matter. If I did it in terms of sets or in terms of, oh, I like the way it said it in sets. Okay, that's okay. So I wrote it in terms of sets, probably because sets look nicer. Okay, so the probability of A union B union C, so the probability of all of this here is the probability of A plus the probability of B plus the probability of C, but you've got a lot of overlap, right? I had, this overlap, and I had this overlap, and I had this overlap. So there's a whole bunch of overlaps here that I've done. So I got to take them away. So let's take away A intersect B, A intersects C, B intersects C. Let's take those guys away. But then I've taken this away too many times, so I have to add it back in. So plus the probability of A intersect B intersect C. So let me give you the addition rule for n events. So the inclusion exclusion principle. The probability, and here I guess I wrote in terms of unions and intersections. You can write in terms of ors. So unions just do ors, intersections do the ands. So these would be ands, these would be ors. So the probability of the union, I equaling 1 to n, a sub I, is equal to the sum, k equaling 1 to n, of -1 to the k minus 1 times times the sum for, well, I being some subset of 1, 2, 3 to n, where the length of I is equal to k, the number of elements in I is k, of the probability of the intersection of a sub I, where the i's are in this index set I, capital I. So remember, and this is a repeat, because basically this is the same statement for sets and for events. So the complement of an event, denoted by A to the superscript C, consists of all events in which event A does not occur. So A to the subscript C, A with a little bar, minus A, not A, and this is be a tilde, little tilde A here. For some reason, it's not showing. Yeah, see that? If you look here, right below it says, it's like the second line. There's a little symbol there, tilde A. A prime, not A. This is the event that event A does not occur. As we've seen before, the probability of E is always between 0 and 1. The probability of the complement of E is 1 minus the probability of E. The probability of the complement of E plus the probability of E is just 1. Well, now I switch to A's. A and the complement of A are disjunct. It's impossible for event and its complement to occur at the same time. So this is A, this is the complement of A. And so this is, well, suppose that this gives me the probability of A, then the probability of not A is 1 minus the probability of A. The total area here for your sample space is 1. So, given a standard deck of 52 cards, determine the probability of drawing a queen or a black card. So, let's look. Black. So, there are 4 suits: diamonds, spades, hearts, yeah, and whatever's. Why can't I think diamonds, spades, hearts, clubs, the clubs. Okay, so let's see, the diamonds and the hearts are red, the clubs and the whatever, in spades. So spades and clubs, yeah, those are black. I'm trying to think. It's been a long time since I played with cards, evidently. The spades and the clubs, yeah. The spades and the clubs are black. The diamonds and the hearts are reds. Yeah, that's it. Diamonds, hearts are reds. And so, yeah, 52 cards, 13 of each of the suites. So, of the suits, 13 of each suit. And so, there are 26 black cards and 26 red cards. Queens. There are 4 queens, 1 of each of the 4 suits. So there's 1 queen of of spades, of hearts, and clubs, and diamonds. And so let's figure out the probability that we select a queen or a black card. Well, by the additive property of probability, the addition rule, I have that the probability of queen or black is the probability of queen plus probability of black minus the probability of queen and black. So let's look. 4 out of the 52 cards are queens. 26 of the 52 cards are black. But 2 of the queens are blacks. So you got to get rid of those 2 black queens. Otherwise, you would have been double counting. So notice that I counted the black queens when I was counting queens, and I counted the black queens when I was counting blacks. So you don't want both blacks and queens to be counted twice. So you got to get rid of the black queens. So I get rid of those 2 black queens. And so I have 28 out of the 52 are queens or blacks, or black cards. And so 28, 52. Oops. Let E, F, and G be mutually exclusive events with the probability of E being 0.3, probability of F 0.2, probability of G 0.3. Determine the probability of E or F or G. So I could use this probability of E or F or G. Just add these up, subtract these, add these. Or I could use this inclusion exclusion principle. Or, easier, I could read where it says they're mutually exclusive events. If they're mutually exclusive events, there's no overlap. That makes my life really easy to find the probability of E or F or G, add them up because they're mutually exclusive. Let's add up the probabilities. 0.3 plus 0.2 plus 0.3, 0.8.
Students, it was found that 200 of them had taken a math class the previous semester. And that, so there are 300 students. Of that 200, had taken math, 190 had taken a chemistry class, and that 120 of them had taken both a math and a chemistry class. And so by the find the probability in this class that a student had taken either a math class or a chemistry class. So by the addition principle, the probability of taking a math or chemistry class, probability of taking a math class, 200 out of 300, plus the probability of taking a chemistry class, 190 out of 300, minus the probability that they took both a math and a chemistry class, 120 out of 300. And so if you add this, you get 270 out of 300. So let's look at A given B. So this notation here means A given B is event. That event A occurs given that event V has already occurred. So when you say A and B, that's the event that A occurs and that B occurs. So recall that the probability of at least one is easier to find by looking at the complementary event. The complement, well, let me assume that we're counting. And so if I say at least one, and I'm counting, meaning that it has to be a whole number, then the opposite of greater than or equal to 1 is less than 1. And so just equals 0. And so the probability of at least 1 is 1 minus the probability of none. And so it's easier to look at the complementary event in this case. Topford supplies X data DVDs in lots of 50. And they have reported a defect rate of 0.5%. So the probability of a disk being defective is 0.005. It follows that the probability of a disk being good is 0.995. What's the probability of getting at least one defective disk in a lot of 50? And so let's figure out the probability of getting at least one. Well, let's look at the complementary event. So it's 1 minus the probability of getting less than 1, getting 0, meaning that, well, we're counting the number of defective disks. If X is 0, that means there are no defective disks, meaning that all the disks are good. So 1 minus, and these are independent events. So 1 minus the probability of, well, a disk being good is 0.995, non-defective. So there are 50 of them. So this will be 0.95 to the power 50. So 1 minus 0.995 to the power 50 is 0.2216874429. And that's the probability of having at least one defective disk in a lot of 50. Conditional probability. The probability of E given F is the probability of E and F divided by the probability of F. Or, if I look at it this way, the probability of F given E is the probability of E and F over the probability of E. Notice in this notation, it sort of helps you to figure out, well, what you're dividing by, because this sort of looks like division. And so your quote unquote denominator is F, your denominator is E. So this notation helps you to remember the formula. So you refer to the table to find the probability that a subject actually uses drugs, given that he or she had tested positive for the drug test. And so we want to find the probability that the person takes drugs, given that they tested positive for the drug test. So let's only look at people who have tested positive for the drug test. So when computing conditional probability, easiest way to do it is to restrict your sample space to those occurrences where B occurs. Well, it's A if you're doing A given B. And then figure out of those, how many have that A occurs of those where B has already occurred. So I only look at those who have tested positive for the drug test. 90 plus 44 is 134. Of those 134, 44 of them actually use drugs. And so the probability that you use drugs, given that you tested positive, is 44 out of 134. Suppose you roll a dice twice. So I'm sorry. Suppose that you roll 2 dice. You observe that one of the dice you rolled is a 6. Determine the probability that the sum of the 2 dice is less than 9. So let's think about this for a second. You roll 2 dice. You see one of them is a 6. Well, the only way that the sum of these two could be less than 9 is if the other dice is a 1 or 2. Can't be a 3, 4, 5, or 6. Or, you know, the sum of them would be more than 9. So it can only be a 1 or 2. That's 2 out of the 6. So it can only be a 1 out of 3 chance that you roll, that the second dice that you roll will be a 1 or 2. However, that logic is completely false. That you're not taking into account your additional information that 6 has been rolled. So because of that, your calculation, your conditional, this should be a conditional probability, is a conditional event. Your probability of that conditional event that I just incorrectly logically calculated is, well, it's wrong. You can't, I mean, you know, the sort of led you astray. So let's try to do this correctly. So I'm going to roll 2 dice. So just like before, I can roll 1 dice. It can be 1, 2, 3, 4, 5, 6. The second dice, 1, 2, 3, 4, 5, 6. You're looking at the sum of the 2 dice. So I'm going to add 1 plus 1 is 2. 1 plus 2 is 3, 4, 5, 6, 7, 3, 4, 5, 6, 7, 8, 4, 5, 6, 7, 8, 9, 5, 6, 7, 8, 9, 10, 6, 7, 8, 9, 10, 11, 7, 8, 9, 10, 11, 12. So I notice that I've rolled a 6. So what you do is you roll 2 dice. 1 dice you're able to see, another dice is rolled in back of something, and you're not able to see the value of that other dice. But you're able to see one of the dice. Let's see how that's different than just rolling 1 dice. What I told you before, if you just roll 1 dice, the probability of rolling a 1 or 2 is, well, 1 out of 3. So now, what's the probability of rolling 2 dice? Given that you see a 6, what's the probability that the sum is less than 9, of those 2 dice is less than 9? And so I've rolled a 6. So let me highlight the 6 here. And I want to find the sum being less than 9. So it could be a 7 or an 8, a 7 or an 8. Therefore, the probability of rolling a sum who's less than 9 is 1, 2, 3, 4 out of 1, 2, 3, 4, 5, 6, 7, 8, 9, 10, 11. So the probability of rolling a 9, the probability that the sum of the two dice is less than 9, given that you rolled a 6, is 4 out of 11. It's not 2 out of 6 or 4 out of 12. It's 4 out of 11. So notice that you have to be more careful. So just don't go with your intuition. Actually do the techniques that I've told you. That's why, I have you write out these things like this, so you can actually do the calculation. 8 red balls. Oh, let's see here, wait. I probably have section 4.2, right? One second. Let's see. I probably at least have a picture of the ball. Waiting for this to come up, see if I actually do. Okay. Slowly, wait, okay. It's slowly coming up. Okay, so forget that. Okay, so we have 8 red balls, 4 white balls are placed in a bag. The first ball chosen from this bag is white. Determine the probability that the second ball chosen is, oh, there it is. Of course I don't have it. After all that wait, well, that's unsatisfying. Okay, so, whoops. Okay, so we have the first ball chosen is white. So what's the probability the second ball chosen is red, given that the first ball chosen is white? Well, if I choose a white ball, then there are only 3 white balls remaining. Therefore, the probability of getting a red ball is 8 out of, well, 8 plus 3 is 11. So 8 out of 11. So confusion of the inverse. So this is usually called the prosecutor's fallacy because, well, in most trials, most lawyers, many lawyers are not mathematicians, or they just disregard the fact that they were mathematicians. And it turns out that the usual arguments of prosecutors confuse the conditional probabilities. And so this is usually called either confusion of the inverse or the prosecutor's fallacy. When you incorrectly believe that A given B is the same as B given A. Or you use, as an argument for A given B, use the argument B given A. So, oh, yes. It is known as the prosecutor's fallacy. So don't confuse them. So don't confuse the two. A given B is not the same as B given A. Those are two completely different events. The multiplication rule for probability. The multiplication rule for probability is the probability that E and F is the probability of E times the probability of F given E. Or I could write it this way: the probability of F times the probability of E given F. Two events, A and B, are independent if the occurrence of one does not affect the occurrence of the other. So in this case, A given B is equal to, if A given B is equal to A, then A and B are independent events. Similarly, the probability of A given B is therefore the probability of A. So you don't have to worry about, well, conditional probability. The two events, A and B, are not independent. They're said to be dependent. So I guess I should say that two events are dependent if the occurrence of one affects the occurrence of the other, but this does not necessarily imply that one of the events causes the other event. The multiplication rule of probability for independent events. Suppose that E and F are independent events, then the probability of E and F is the probability of E times the probability of F. So assuming independence, it makes probabilities easy. You just multiply them all together. Such as when people talk about DNA evidence, and usually in courts, they'll say, well, you know, the probability that, you know, your DNA, that this DNA that we tested was not yours, is 1 out of a billion or whatever. The way that they get those probabilities is that they look at DNA of differing people, and they look for what are called markers on your DNA, which are pieces, which are locations on your DNA that do not code for genes. And so there's a lot of parts of the DNA, these regulatory parts of the DNA, the epigenome, things like that, which do not actually code for genes. And so they'll look at this and they'll say, oh, well, you know, if I look here, I see that 1 out of these 20 people that I've looked at have this particular marker on this particular gene. And they look at several markers together. You know, maybe there's 20 markers. And so they'll multiply the 20 times, or maybe they're 30 markers. And they'll multiply the 30 times the 20, and they'll get a gigantic number. Of course, when they do that, they're assuming independence. Now, the problem is, of course, is that people are not independent of each other. The DNA of people is not independent of each other. You have DNA that's very similar to your parents, very similar to your brothers and sisters, etc. So, humans in general are very related to each other. So their DNA is actually quite related to each other, more related than most other animals around. And so because of that, the independence assumption is not valid. The latest I heard, when they actually did it on a population sample, more or less for those markers that they use for DNA evidence, rather than being 1 out of a billion, it's closer to 1 out of 50,000. You still have to, it's still very unlikely. In other words, DNA evidence is still very, very good. It's just not as perfect as one is misled by. So it's very, very good. 1 out of 50,000, 1 out of, close, 80,000, whatever it turned out to be, is still extremely good. You'd have to still sort of, say why. You still have to sort of explain, why your DNA is there, but it's not like 1 out of a billion. It's much less than that. Okay, so let's do the following. A problem in statistics is given to 3 students, A, B, and C, whose chances of solving it correctly are 1/3, 1/4, 1/2, respectively. What is the probability that the problem will be solved correctly if they all try to solve it independently? And so, let X denote the random variable that counts the number of students that solve the problem correctly. So, the assumption here of independence means that the fact that one student A, solves it, does not influence the fact that students B and C solve it, meaning they're not exchanging answers. They're not cheating. So we're making this non-cheating assumption that, the fact that one student solves it doesn't affect the fact that other students solve it. So let's do this. So I have here student A, student B, and student C. So let's start first. So I want to figure out the probability of at least one solving it. The probability that X is greater than or equal to 1. So let's try to figure out each of these probabilities. So let's first figure out, first go from the inside and then go outwards. So go the innermost and then go outwards from the innermost. So the probability that A solves it is 1 out of 3. Probability that B solves it is 1 out of 4. Probability C solves it 1 out of 2. So 1/3. So the probability that A, B, and C solve it, well, they're independent. Since they're independent, I can just multiply 1/3 times 1/4 times 1/2. So 3 times 4 times 2, 12 times 2 is 24. So 1 out of 24. So the probability, here it is, that A, B, and C solve it is 1 out of 24. Now, let's try to figure out, so I did the innermost. So now let's try to figure out this. Well, let's look at the probability that A and B solve it. If I do that, it's this slice of the pie. So it's this slice here. 1/3 times 1/4 is 1 out of 12. So this whole slice here is 1 out of 12. 2 out of 24. This whole thing here is 2 out of 24, but this little piece here is 1 out of 24. For this is 1 out of 24. And so to figure out the probability of A and B, but not C, you do the 1/3 times 1/4, but then subtract from it what you had from before. Let's do this one. Probability of B and C. Well, 1/4 times 1/2 is 1/8. 3 out of 24. Minus this 1 out of 24 is 2 out of 24. Oh, here it is. And so it is 3 out of 24 minus 1 out of 24 is 2 out of 24. Next, And that's just up there. Probability of A and C, 1/3 times 1/2 is 1/6. So this whole slice here is 1/6, which is 4 out of 24, minus 1 out of 24 is 3 out of 24. Okay. So now let's try to figure out this guy. Well, this whole thing here is 1/3, 8 out of 24. Subtract these to get this. 8 minus 3 is 5, 4, 3 out of 24. Okay, next. Oh, good. Now I can show this guy. So next. This whole thing is 1/4, which is 6 out of 24. Oh, there it is. Which is 6 out of 24. Subtract 2 out of 24. Minus 1 out of 24, minus another 1 out of 24. So 6, 4, 3, 2 out of 24. And lastly, let's figure out this guy here. So this is 1/2, 12 out of 24, minus 3 is 9 out of 24, 8 out of 24, 6 out of 24. So this is 6 out of 24. Okay. Now, 3 plus 1 is 4, 6, 9, 10, 12, 18 out of 24. Therefore, the guy on the outside is 24 out of 24 minus 18 out of 24, 6 out of 24. So now let's figure out the probability that X is equal to 1. Well, let's look at all the ones. This guy, and this guy. That only one person solves it. So notice only A solves it, only B solves it, only C solves it. Let's add up. So 5, 11 out of 24. The probability that exactly 2 solve it. Well, this guy, and this guy. That A and B solve it, B and C solves it, only A and C solves it. So 1, 3, 6 out of 24. Probability that all 3 of it solve it, well, there it is, 1 out of 24. So I'll have to add these up. 11, 17, 18 out of 24. Okay, good. So an alternative solution could be, well, I could use there it is, the inclusion-exclusion principle. So I could use the inclusion-exclusion principle from last week, this. And so the probability of A or B or C is the probability of A, 1/3 plus probability of B, 1/2 plus probability of C, 1/2. I'm sorry, probability of A, 1/3, probability of B, 1/4, probability of C, 1/2, minus the probability of A and B, so 1/3 times 1/4, probability of B and C, 1/4 times 1/2, probability of A and C, 1/3 times 1/2, and probability plus the probability of A, B, and C, 1/3 times 1/4 times 1/2. And so if you add these all up, you get 18 out of 24. Yet another alternative solution, which is, why didn't I remember what I said at the beginning of class, which is to find the probability of at least 1, I should be looking at the complementary event. Remember, the complementary event is many times much easier. So the probability that X is greater than or equal to 1 is 1 minus the probability X is less than 1. So in this case, the probability X is 0. So I don't want any of them to solve it. So the probability that A does not solve it, and B does not solve it, and C does not solve it. These are independent events, remember? I'm assuming that, that there's no cheating going on here. Since there's a 1 out of 3 chance that A solves it, there's a 2 out of 3 chance that they do not. Since B has a 1 out of 4 chance of solving, it has a 3 out of 4 chance of not solving it. Since C has a 1 out of 2 chance of solving it, it has a 1 out of 2 chance of not solving it. So 6 over 24. Subtract that from 1, 18 over 24, and you're done. Notice this is much easier than any of these gigantic type things that I did here. Now, of course, if it was instead, what's the probability that exactly 2 people solve it? Then you'd have to go through something this big. But, or you could do, well, another calculation in you doing that. But again, you have to go through almost the whole calculation. But certainly doing it for at least one is very easy, because finding out the probability that no one does it is going to be very easy calculation. Suppose 50 drug test results are given to people who use drugs. 44 test positive, 6 test negative. There are 50 total results. If 2 of the 50 subjects are randomly selected without replacement. So you take one and then you take another one. Find the probability that the first person tested positive and the second person tested negative. So let's do that. Note that the probability that the first person tests positive is, well, 44 out of the 50. And the second person tests negative. Well, we've already picked one of them, and one of them tested positive. So there are only 43 positives remaining. The second person tests negative. So 6 of the remaining 49 tested negative. And so multiply 44 times 6, 132, 50 times 49. Well, cancel, I guess. Because that's not, no, yeah. So you have to do that's you divide by 2. Divide both, I don't care. Let's say divide each of these by 2. So 22 times 6, 132, 25 times 49, 1225. When 2 different people are randomly selected from those in your class, find the indicated probability by assuming birthdays occur on the same day of the week with equal frequencies. Probability that 2 people are born on the same day of the week. Probability that 2 people are born on Monday. So the probability, well, first, what's the probability that someone was born on a day of the week? Well, 1. So you were born sometime. So 1. What's the probability that the second person was born on that same day? Well, there are 7 days in a week. One of them is the day that you were born. The first person was born. And so 1 out of 7. Now let's do the probability that 2 people were both born on Monday. Well, and of course, I'm assuming independence. The fact that someone in class was born on a particular day does not affect the fact that someone else was born on a particular day. So that's my assumption. Well, let's look at this first person. The probability they were born on Monday, well, there's 7 days in a week and only one Monday, so 1 out of 7. The probability the second person was born on Monday, again, is 1 out of 7. Times 1 out of 7 gives you 1 out of 49. Suppose you have a deck of 52 cards. The first card that you draw is a king. What's the probability that the second card that you draw is a face card? Well, if you look at a deck of cards, a king has a face, so does a jack and a queen. So there are 3 suits, and then, well, it could be diamonds and, spades and hearts and clubs. So there are actually 12 differing face cards in a deck. So the first card that you draw is a king. So there are only 11 remaining cards that have face cards out of the deck of only 51 cards remaining. So what's the probability that you draw, that the second card that you draw is a face card? Well, there are only 11 face cards remaining out of the remaining 51 cards. So 11 out of 51. I'm assuming that once you pick a card, you don't throw the card back into the deck. That you pick a card and you still keep it in your hand. You're drawing cards. Suppose you randomly select an adult from the following. So 500 males are employed, 200 females employed, a total of 700. 50 males are unemployed, 250 females are unemployed. What is the probability that an adult is unemployed given that the adult is male? So I'm given the adult is male. So let me only look at males. What's the probability that the adult is unemployed? Well, 50 of those 550 adult males is unemployed. So first I restrict my sample space to what was given, that they were male. And then I look how many satisfy that the other condition, that they are unemployed. A piece of equipment will function only if all 3 components, A, B, and C, are working. The probability of A failing during the first year is 0.15. That of B failing is 0.05. That of C failing is 0.1. Suppose that each component works independently of each other, so that the failure of any of these 3 components does not affect the workings of the other 2 components. What is the probability that the equipment will fail before the end of the year? So let the random variable X count the total number of components that fail. I want to find the probability that the equipment will fail. Again, everything has to be working. So 1 component failing means the equipment fails. So I want to figure out the probability that X is greater than or equal to 1. Now, again, I could go through this big calculation like I did here, but just like what I did there, it's much easier to do the complementary event. So let's look at the complementary event. So 1 minus a probability of none of the components failing. And so 1 minus, let's see, we have 0.15 probability that equipment A, or component A, fails. Therefore, we have we have an 85% chance that the component does not fail. Since there's a 5% chance that B fails, there's a 0.95% chance it does not fail. Since there's a 0.1% chance that component C fails, there's a 90% chance that C does not fail. So you multiply those together and you get 0.27325. Now notice that this is much faster and easier because we